Today we'll be looking at RLC series circuits. Now we have considered the individual behavior of inductors and capacitors. Today we are going to be looking at the combined effect of having these elements in the same series circuit. If we consider the circuit shown, the resistor being connected in series with the capacitor and the inductor. Now, we see that the voltage across the inductor, capacitor, and resistor, when added, would give us the supply voltage. All right. Now, based on the individual characteristics, we're going to be looking at the phase relationships between the voltages of these three elements and the circuit current. So the circuit current, IS, is in phase with the voltage across the resistor. And so they would be along the same path. So voltage across the resistor is in phase with the circuit current. If we consider the inductor, we know that the inductor, the voltage across the inductor, lags the current by 90 degrees. So here's our inductor voltage. And also, for the capacitor, the current leads the voltage across the capacitor by 90 degrees. And so we have here VC. So we have all three voltages represented. Now we're going to make an assumption, and that is just for the purpose of explaining this, the relationship. We're going to assume that the voltage across the inductor is larger than the voltage across the capacitor. Now this is a pure assumption, it doesn't have to be. However, if that were the case, then finding the resultant voltage along the vertical, yes, the resultant voltage along the vertical, if VL is greater than VC, yeah, would be along VL. But I'm trying to find the resultant of all three. As we said before, the supply voltage is the sum of the voltages across the resistor, the capacitor, and the inductor. So I now find the resultant of all three. And there we go. And so Vs would now be that resultant. And I can use Pythagoras' theorem to determine the relationship between Vs, Vr, and the difference we have here, VL minus Vc. Let's do that. Vs squared is equal to Vr squared plus VL minus Vc all squared. And we therefore have an expression for Vs, which is equal to the square root of Vr squared plus VL minus Vc all squared. And if we substitute for the voltages by putting in the current, for the resistor voltage, we have IR. For the inductor, we have IXL. And for the capacitor, we have IXC. If we make those substitutions, yes, and of course for Vs, we have IZ. Make those substitutions and simplify, we get that the impedance of this RLC circuit is equal to R plus J into XL minus XC all squared. For the phase angle phi, which we are showing here, the phase angle phi, we know that tan phi is equal to XL minus XC over R. So phi is equal to the inverse tan of XL minus XC all divided by R. So the best way to try and understand this is by jumping into an example. So here is our circuit. We have here a series connection of an 8 ohm resistor, a 530.5 microfarad capacitor, and a 38.2 millihenry inductor connected across a 30 volt 50 hertz supply. We want to determine the current flowing. Now we first need to find the impedance. Now we know that the impedance is equal to the square root of R squared plus XL minus XC all squared. And of course, XL is equal to 2 pi FL, which is 2 pi times 50 times 38.2 times 10 to the minus 3. And that gives us 12 ohms. XC is equal to 1 over 2 pi FC, which is equal to 1 over 2 pi times 50 times 530.5 times 10 to the minus 6. And this gives us 6 ohms. So Z, our impedance, is equal to the square root of 8 squared plus 12 minus 6 all squared, which is equal to the square root of 8 squared plus 6 squared, which is equal to 10 ohms. So our impedance, the magnitude of our impedance, is 10 ohms. But we also need to determine the phase angle. So the phase angle phi is the inverse tan of XL minus XC over R, which is equal to the inverse tan of 12 minus 6 over 8. It's the inverse tan of 0.75, which is equal to 36.86 degrees. So the magnitude of the current I is equal to V over Z. And so we have that I is equal to 30 over 10. That's the magnitude, which gives us 3 amperes. For phi, we need to think carefully about this. Now, we know that XL is up there, XC, and R. So given that XL is greater than XC, it means that phi would be here. Or in other words, phi would be positive. Okay. And this would be V, and this would be my I-axis. So I is therefore equal to 3 amperes at 36.86 degrees lagging. And why do we say lagging? Because I, or the phase angle, phi, is always given as the current relative to the voltage. So in this instance, we because it's inductive, the current would be lagging the voltage since positive rotation is counterclockwise. Again, thank you for your attention and look forward to providing you with more information in our upcoming series. Thank you.